Well, hello there, stats fans. Today we're going to be doing some really important skills, really the most important skills, I believe. Most people would probably say these are the most important skills that you're going to learn from a stats class. We've already teased out the normal distribution, and today we're going to take a closer look at the normal distribution and see how it's really used in statistics. So let's go ahead and check it out in the next screen. We've got, will Marty make it back to the future? And after accelerating for 20 seconds, a DeLorean sports car has a wide range of speeds it can achieve depending on traction. The distribution of speeds follows an approximately normal distribution with a mean of 80 and a standard deviation of 7.7. So part 1 here says to label the appropriate values on this normal distribution. So this is what the normal distribution looks like. We're going to keep writing standard deviations above the normal curve. And below the normal curve, we're going to be putting numbers in context. For example, in this DeLorean sports car, the mean is 80. So right down at the bottom, underneath 0 standard deviations, we're going to write the number 80 because 80 is the mean, and the mean is 0 standards deviations away from the mean. Now, if we know that the standard deviation is 7.7, we can label a couple of more points here. Again, 1 standard deviation above the mean, from 0 to 1 standard deviation, that's going to be 80 plus the mean of 7.7, which gives us 87.7. Now, on the other side of things, at a negative 1 standard deviation, that's just going to be the mean minus 7.7, which is 72.3. Of course, we can do this process again. If I do the mean, 80, plus 2 times the standard deviation, that'll give me the score at 2 standard deviations, which is a speed of 95.4 miles per hour. And if I do 80 minus 2 times the standard deviation, I get the negative 2 standard deviation score, which is 64.6, or the negative 2 standard deviation speed, 64.6. And of course, this curve goes all the way from negative 3 to positive 3. So we're going to do this one more time. And now we have the speeds that are at 3 standard deviations above and below the mean. The mean of 80 minus 3 times 7.7, that is 56.9. And then the mean of 80 plus 3 times 7.7, that says 3 standard deviation speed, 103.1. So that labels the curve, and that kind of lets us know a little bit about these speeds. Any speed that's between 72.3 and 87.7, we would say that that is within 1 standard deviation of the mean, which is something that you probably heard of a whole bunch of times, but now you kind of know what it means. Anything between 80 and 87.7, that is 1 standard less than 1 standard deviation above the mean. Anything between 64.6 and 95.4 miles per hour, that's within 2 standard deviations of the mean. Anything less than 64 and greater than 95, that would be more than 2 standard deviations away from the mean. And then, of course, really far at the end, we've got the 3 standard deviation scores. So that's the kind of things that we would be saying: within 1 standard deviation, within 2 standard deviations, more than 2 standard deviations away, more than 1 standard deviation away. And this is a probability distribution. So anytime we compute area, we can just compute probability at the same time. Probability and area are the same thing for a probability distribution. So what percentage of runs will give the DeLorean a speed greater than 87.7? So let's take a look at that. We learned on the last lesson that anything within 1 standard deviation of the mean on a normal curve that has an area of 68%. Now, if I just take a look at if I take a look at half of this area, so between 80 and 87.7, would get me half of the area, or just 34%. And if everything above the mean of 80 is 50%, then anything in that blue area has to be 16%. So the area of the blue area is 16% because 34% and 16% add up to 50%. And now just taking a look at the blue area, this says that anything greater than 87.7, all the way really to infinity, that has an area of 16%. So the percentage of runs of a DeLorean with a speed greater than 87.7, that's going to be 16%. Now, I'm very particular about how I want you to write things. So here's exactly how I want you to write this. That P means either probability or proportion. It's kind of interchangeable in this case, but let's just say proportion of of runs that are greater than 87.7. That's equivalent to the proportion on the Z curve. Just write the Z for now. We'll talk about what that means. The Z greater than 1, and that's equal to 0.1600. So at the end of this, I would like 4 decimal places. Now, the only possible exception to the 4 decimal place rule is if you have trailing zeros. In this case, we have trailing zeros. We have 2 zeros after the 0.16. So that's the only time it's acceptable for you to omit them. So that's how we want those written. And that's how we do our very first area. We did that all using the 68, 95, 99, 7 rule. In fact, we only used the 68 part of the 68, 95, 99.7 rule. Okay, next, let's figure out the proportion or the percentage of runs that will give the DeLorean a speed of between 64.6 and 87.7. So the first thing I want to observe is if I shade in the area, I notice that I'm going between a Z-score, 2 standard deviations below to 1 standard deviation above. Now those aren't the same. Like if I went between -1 standard deviation and +1 standard deviation, then immediately I know that would be 68%. But because these are different, -2 and +1, I can't really use that method. So if that happens, and I have a positive standard deviation and a negative standard deviation, I'll split up the area. So I'm splitting it up between values or parts of the area that are below the mean and parts of the area that are above the mean. Now, I already know the blue thing because we did this yesterday. Or no, we did that actually just a few moments ago. Between a standard deviation of 0 and a standard deviation of 1, that was 34%. And remember that 34% is half of the 68% because we're only looking at between 0 standard deviations and 1 standard deviation. Now on the other side, the yellow one, I don't really know this yet, but I know that within 2 standard deviations is 95%. Just like with the 34%, within 2 standard deviations is 95%. I'm only taking the lower half, so I have half of that 95%, which is 47.5%. So I'm ready. All I need to do is add those 2 numbers together, and that will give me the area that I'm looking for, or the percentage that I'm looking for. Let's write that down over here. So the percentage of runs that are between 64.6 and 87.7, that's equivalent to the area between 2 standard deviations below the mean and 1 standard deviation above the mean. And that's equal to 34 plus 47.5, and that's 81.5%. Okay, let's move on to question 4, and that is what percentage of runs will have a speed less than 64.6? So let's go ahead and move up to our map. Less than 64.6, we want to highlight that. And I'm going to leave the stuff that I've done before here, and I'm going to highlight less than 64.6 in green. Now the part that I don't need is at 34%, so let's get rid of that. Now looking on the left half of this normal curve, I notice that I have 2 areas that should add up to 50%. So that remaining green section there, that's just 2.5%, because at 2.5 plus the 47.5, they need to add up to 50%, because that's everything below the mean. Now let's take away that 47.5, and that gives me all the area I need, 2.5%. So we're going to come back down here and we're going to practice writing again. What percentage of runs will give the DeLorean a speed less than 64.6? The percentage of runs that are less than 64.6, that's equivalent to the area under the Z curve, that's less than -2, and that's 2.5%. Finally, what percentage of runs will give the DeLorean a speed less than 68.45? Okay, 68.45. Oh my gosh, 68.45. That's nowhere on this map, is it? Okay, let's get rid of that green area because we don't need that. And then let's kind of guesstimate where 68.45 would be. So the speed 68.45 miles per hour should be somewhere between the speed of 64.6 miles an hour and 72.3 miles per hour. I want to know the percentage of runs that are less than 68.45, so I need to highlight all of the speeds that are less than 68.45, which would be what we see in yellow. Now it's hard for us to figure this out because we actually don't know the Z-score, or we don't know how many standard deviations away this is from the mean. But we can certainly figure that out. Let's see. How many standard deviations away from the mean? Well, the first thing we need to know is how many miles per hour below the mean it is. In order to figure that out, we can just do the speed minus the mean, which would be 68.45 minus the mean of 80, which is 11.55, negative 11.55. So that negative signifies that we are below the mean. And if I want to turn that into standard deviations, I just need to divide by the standard deviation speed. And what I get is negative 1.5. That negative 1.5 is what we call a Z-score. The Z-score just tells me how many standard deviations above or below the mean any particular speed is. So a positive Z-score means that the number, our contextual number, is above the mean. A negative Z-score means our contextual number is below the mean. So we are 1.5 standard deviations below the mean because our Z-score is negative 1.5. So you might be asking, well, how do I figure out the area? Because the 68, 95, 99.7 rule isn't going to work here. And that's where the calculator comes in. So there is a function on the calculator that will give you the area on a Z curve, on a normal curve, given two Z scores. So in order to get there, we have to push second and then vars. And we're going to use this thing called NormalCDF. So NormalCDF is going to ask you for two z-scores, the lower z-score and the upper z-score. Now for our area, we don't really have a lower z-score because if we take a look at our area, we are going all the way here to negative infinity. Since we're going to negative infinity, on our calculator, we need to put a really small number. And the smallest number your calculator has is that -1 EE99. So I'm going to practice putting that in there with you. The negative number, the negative button, the 1 button. Now EE is second, and then the comma. That gives you that little lowercase e to the 99th power. And basically, this is equivalent to -1 times 10 to the 99th power. It's in scientific notation. Now the upper z-score, or the right side of our interval, that's at -1.5. The mean of a z-score of the z-curve is, or of a normal curve, is 0. The standard deviation of a normal curve is 1. So we push paste and enter, and that's our area, 0.668. Now, just like before, I want this number in 4 decimal places, so 0.668. The other thing that I should mention is that whenever you're writing out a z-score, your z-score needs to be at 3 decimal places. And since I've been using z-score so informally, now's a good time to say that the z-curve, anytime we say z, that's synonymous with the normal curve. Another name for the normal curve is the z-curve. A z-score is a relative position on the z-curve, or a relative position on the normal curve. So this all kind of works together. Number 5 is such an important skill for you. What you're writing down, how you're writing it down is very important. So, really focus in and try to perfect what we're doing here. So let's move on to number 6, and this is more skill. This is kind of the same one. What percentage of the runs has a speed greater than 85 miles per hour? 85 is not a z-score, or is not an integer z-score. So we'll have to get a z-score. So any z, that's equal to the contextual number minus the mean divided by the standard deviation. That gives us 0.649. That's our 3 decimal place rule. So we want the proportion of runs that are greater than 85 miles an hour. That's equivalent to the proportion on the z-curve that's greater than 0.649. Remembering that z-curve is a normal curve. And that's equal to something that my calculator is going to tell me. So we'll get to the calculator now, and we'll do second distribution, NormalCDF. This time, let's take a look at the area. This time I want speeds that are greater than 85 miles per hour, which is equivalent to a z-score of 0.649. And above that means that I need to shade to the right. So this is the area shaded to the right. And we can tell now that the lower bound of the area is 85 and the upper bound of the area is infinity. So when I get back to my calculator, for the lower, I'm going to put that z-score 0.649. And for the upper, I'm going to put that infinity. Now there's no infinity symbol, so you need to put 1, second, comma, 99. The mean of the normal curve is 0. The standard deviation of the normal curve is 1. Paste. And that gives me an area of 2582, which I'll notate in my work. Now, one thing that we should also talk about while we're here is you notice that in the calculator that there is a place for me to put in the mean and the standard deviation, which means there's another way of doing this. If I want to know all of the speeds that are greater than 85 miles an hour, upper limit is still infinity, the mean is 80 and the standard deviation is 7.7, I can crunch this number as well, and I should get something that's very close. Actually, this also rounds to 2581. So, not also. So this is accurate within like that fourth decimal place. So really close, depending on which one you use. If you're in my class, as long as you are in that, really close to that, or I can tell where that number came from, you're going to be okay writing down either of them. This trick that we showed just right here, this is good for a multiple choice test. Okay, so are we having fun yet? We're really using our calculator the way it's intended to be used for this class. So let's move on to question 7. And now we want to know what percentage of runs will give the DeLorean a speed between 70 and 95. Let's go back to our normal curve and let's find 70 and 95. Those are my approximate places for 70 and 95. We'll shade in the area. So we notice that 70 and 95 are not integer z-scores. So let's turn those into z-scores down over here using the same z-score transformation. Z-scores are equal to our numbers, our speeds, minus the mean speed, divided by the standard deviation of the speeds. And that's equal to negative 1.299 and 1.948. So we can go right back up to our diagram. And let's put our z-scores there. And now that I have those into my region, I can see that I want the area between negative 1.299 and a z-score of 1.948. So when I get to my calculator, I'm going to start over here. Distribution, NormalCDF. The lower is negative 1.299. The upper is 1.948. Paste that, and that gives us an area of 8773. So the proportion of runs that are between 70 and 95 miles an hour, that's equivalent to the area on the normal curve between a z-score of negative 1.299 and positive 1.948, and that's 0.8773. Incidentally, since we're working on the calculator a lot, you should know that you never need to write down your calculator work on your paper. There's always a way of writing it using statistics. If you write your calculator stuff on your paper, then there are some certain set of rules that you need to follow, which we can definitely talk about in class. But for almost everybody out there, you don't need to write down your calculator work. Just write down the probabilities. Last one. Marty wants his last run to be in the top 15% of all possible speeds. So what speed does he need to achieve to be in the top 15%? Now this is different because we know the percentage or the area, it's 15%, but we don't know the speed. So this is a reverse situation of what we had before. Looking at the normal curve, we know the area this time, but we don't know the speed and we don't know the z-score. So we have to work backwards in order to figure that out. And going to my calculator, there is a function which lets us go backwards on the normal curve from an area to a z-score, and that is inverse norm. So in inverse norm, we need to put in the percentile rank. Notice that here we have 15% above our speed, which means that we have 85% below our speed. So in this calculator, we need to put 0.85, and that'll give us speed, the appropriate z-score. I'm gonna go down here and copy and paste, and that tells me that the z-score is 1.0364. Now when we write this, what we're going to do is we're going to leave blanks in our statement. So the proportion of speeds greater than some unknown number, that's equal to the proportion on the z-curve that's greater than some unknown number, and that's equal to 0.15. So we can fill in these numbers now using what we just found out on the calculator. Now the z-score was 1.036. Let's go back to the calculator again and let's get the speed now. So we're going to go to, oops, wrong one, second vars, inverse norm. And this time we'll change this to a speed of, the mean speed is 80. The standard deviation speed is 7.7. And we'll paste that along. And now we'll get a contextual number, which is 89.98. Actually, that should be rounded to 88. Normally we would say 88.9, but that 9 rounds to an 88. So we're saying that the speed greater than 88 miles an hour will be in the top 15%. A speed of 88 miles per hour or greater will be in the top 15% of all runs. So just in summary of your calculator work, if you know the z-score but you don't know the area, you want to use the NormalCDF. If you know the area or the percentile, and you don't know the z-score or the context, then you need to use inverse norm. And that ends probably the most important lesson you've had in AP Stats up till now. So let's get to our big ideas. First of all, we've got the idea of a density curve where area is probability. That's the thing that makes this entire thing go. We've got a z-score, which is the same thing as the number of standard deviations above and below. We've got TI notation. How do we find the area, and how do we find a z-score or a value? Remember that we need to put a percentile rank into inverse norm. That's very important. And reminders: draw the curve, label n mean standard deviation. That means a normal curve with a mean and a standard deviation. And then show those equations. Check our understanding now. When professional golfer Jordan Spieth hits his driver, the distance the ball travels can be modeled by a normal distribution with a mean 304 and a standard deviation of 8. So on a specific hole, Jordan needs to hit the ball at least 290 yards to have a clear second shot that avoids a group of trees. What percentage of shots will travel at least 290 yards? So I'm going to start things out by looking at my normal curve. Let's make this a little bit bigger. And let's label. We need to get to 290, which is a little less than the mean. So you don't need to label all of the numbers. You maybe just the mean and one other. So I know the mean is 304. 290 is less than 304. So let's count our standard deviations backwards. 304 minus 8. That's 296. I need to get to 290, so let's do this again. 296 minus 8 yards. Okay, that's 288. Now I know exactly where 290 is, so I'm going to draw that in. And then I'm going to shade in the area that's at least 290 yards. So now that gives me a pretty good idea about the area I'm looking for. I know that the area's got to be bigger than 50% plus a 34%. So it's got to be bigger than 84%, but it's got to be less than, I think that's going to be 97.5. So somewhere in that range, somewhere between 84 and like 97. The z-score is equal to context minus the mean divided by standard deviation, which is 290 minus 304 divided by 8, which is negative 1.750, but I guess we don't need the 0. Now we'll start in with our probability. The proportion or the probability of drives that are greater than 290, that's equivalent to the proportion on the z-curve that's greater than negative 1.75. Grab our calculator, maybe clear off a little bit, and go to our distribution menu. And we want to know between negative 1.75 and infinity. That's 1 second, comma 99. The mean for a normal curve is 0. The standard deviation for a normal curve is 1. Paste that on there. Oop, something went wrong. Push go to, and I bet I know it's that. Yeah, I pushed a minus sign instead of a negative sign. Let's change that to a negative sign, and that will give me 95.99. And then now it's nice to write a summary sentence. So at least 96% of Spieth's drives are, about 96% of Spieth's drives are at least 290 yards. Now the point I want to make here is that once you have written your 4-decimal number here, 9599, then feel free to round it in your summary sentence. That takes care of number 1 and check your understanding. Let's do number 2. On another hole, Spieth has the opportunity to drive the ball onto the green if he hits a distance in the top 10% of his drives. How far does this ball need to go? So this is that reverse situation again. We know it's 10%, but we don't know what the number is, and we don't know what the z-score is. So I'm going to go ahead and get that normal distribution out there. Let's estimate 10%. Now I've done this a few times, so I know where 10% is. It's right around closer to 1 than 2. You will probably put it somewhere else, but that's kind of where that 10% goes, again, just by experience. Let's write in a few numbers here. Let's put the mean. Then now looking at what I have written here, we can kind of guess that his drive needs to be somewhere between 312 and 320, maybe like 314. Okay. I'm going to write down the probability. I'm going to leave the blanks in there so that you can get used to that. So the only number that we know about is this 10% at the very end here. We don't know the z-score. We don't know the drive length. We just know the 10%. So that's a signal for me that I should be using inverse norm. So let's grab inverse norm. Always do it from the home screen. And we want the area to be 0.9 because the area on the left, you have to put in as a percentile rank. So the area on the left is 0.9. Mean is 0. Standard deviation is 1. So that gives me a z-score of 1.282. To find the drive length, we're going to put in our contextual mean, which was 304, and our contextual standard deviation, which was 8. And we'll hit that again, and that gives us 314.3. Now we'll go to our paper and we'll backfill the things that we didn't know. We now know that the drive length is 314.3, and we know that the Z-score is 1.282. And a ball must be driven at least 314.3 yards to be in the top 10% of Speed's drives. So that's our lesson today. I think we went a little bit long. Yeah, that's 35 minutes. But I think it's important because, these normal distribution skills are really the ones that should be sticking with you, at least from this first semester of AB Statistics. So that's it. I'm out of here. Have a good day and see you on the next one.